Let's get ready to explore. Number 10. Saturn's perfect hexagon. In 1981, NASA's Voyager 1 spacecraft swept past Saturn and transmitted something back to Earth that stopped scientists cold. Locked at the planet's north pole, carved into the cloud tops with geometric precision, was a six-sided storm so mathematically perfect it looked less like a weather system and more like something had drawn it there on purpose. Every planet with an atmosphere has weather, storms, vortices, pressure systems, the churning chaos of fluid dynamics playing out across millions of square kilometers. Scientists understood this. Jupiter has its great red spot, Neptune has its dark storms, and Earth has its hurricanes. Weather is messy. Weather is irregular. Weather does not arrange itself into a flawless hexagon wider than 4 Earths side by side, and then hold that shape for over 40 years. The hexagon sits at approximately 78 degrees north latitude on Saturn. Its sides measure roughly 14,500 kilometers each. Its total width stretches about 32,000 kilometers, and the jet stream forming its edges moves at speeds approaching 320 kilometers per hour. Inside it, multiple vortices spin in alternating directions. At its center, a hurricane-like storm rages continuously. The entire structure rotates with a period of precisely 10 hours, 39 minutes, and 24 seconds, perfectly synchronized with Saturn's own internal radio emissions. NASA's Cassini spacecraft observed it from 2004 until 2017, watching it shift in color from a deep blue to a hazy gold as Saturn's seasons changed. Laboratory experiments and computer models have reproduced hexagonal shapes in rotating fluids under very specific conditions, but none has fully replicated all the observed properties simultaneously. The precise geometry, the extraordinary stability, and the absence of any equivalent structure at Saturn's south pole. Astronomer David Godfrey first formally described this structure in 1988 after painstakingly reconstructing the Voyager imagery. Nearly 4 decades later, scientists still cannot fully explain why a gas giant's atmosphere decided, of all possible shapes, to build a perfect hexagon and then refused to change it. Number 9. The tilt of Uranus. Every planet in our solar system spins like a top. Some lean a little, some lean more, but they all spin with their poles pointing generally upward, perpendicular to the plane of their orbit. Then there is Uranus, discovered by astronomer William Herschel in 1781, which does not spin at all. It rolls, tilted at a staggering 97.8 degrees, orbiting the Sun essentially on its side for reasons that remain, after more than 2 centuries of study, genuinely unresolved. The planets formed from the same rotating disk of gas and dust, and basic conservation of angular momentum means they should all spin with a similar orientation. Most do. Earth tilts at 23.5 degrees, Mars at 25 degrees, Saturn at 27 degrees. Even those modest tilts required explanation, attributed to ancient collisions during the chaotic early solar system. But Uranus is not tilted at 25 degrees. It is tilted at nearly 98 degrees, which is not a lean, but a complete toppling, and no other giant planet comes close to matching it. What deepens the mystery is the moons. Uranus has 27 known moons, and every single one of them orbits at the same extreme tilt as the planet itself, meaning the entire Uranian system is rotated together. The leading explanation has long been a catastrophic collision with a body 1 to 3 times the mass of Earth during the solar system's violent formative period, a collision powerful enough to knock the planet onto its side. But simulations of such an impact consistently struggle to reproduce the moon system we observe, because a single giant impact should have left the existing moons orbiting in their original plane. In October 2022, a new study proposed an entirely different mechanism. A large moon, long since destroyed, that gradually destabilized Uranus gravitationally over hundreds of millions of years before crashing back into the planet and locking its tilt at 98 degrees. Uranus also emits far less internal heat than Neptune, despite the two planets sharing nearly identical sizes, masses, and compositions, and that discrepancy may be a scar left by whatever happened. No spacecraft has visited Uranus since Voyager 2's single flyby in January 1986. The sideways planet remains one of the most neglected objects in our solar system. Something catastrophic happened to it billions of years ago, and the evidence has been quietly rolling around the sun in plain sight ever since. We just cannot agree on what it was. Number 8. The bright spots of Ceres. In February 2015, as NASA's Dawn spacecraft made its careful approach to Ceres, the largest object in the asteroid belt, mission scientists watched the dwarf planet come into focus for the first time in history. What they expected was a cold, cratered, unremarkable rock. What they got, emerging from the darkness at the center of a large crater, were two intensely brilliant white spots blazing back at them like headlights in the void. Ceres sits in the asteroid belt between Mars and Jupiter, roughly 414 million kilometers from the Sun. At that distance, with no significant tidal heating from a nearby gas giant and no thick atmosphere to trap warmth, it should be geologically inert, cold, frozen, dead. Scientists expected Dawn to document craters and measure composition, the quiet archaeology of a primordial leftover from the solar system's formation. The bright spots were not part of any prediction. Dawn entered Ceres orbit in March 2015 and began the slow process of spiraling closer. The spots resolved into two distinct features inside a 92-kilometer-wide crater called Alcator, later named Cerealia Facula and Venalia Faculae. Their albedo, the measure of how much light they reflect, registered at approximately 40%, roughly 4 times brighter than the surrounding surface. A faint, localized haze periodically appeared above them, suggesting active outgassing. Something inside this cold, distant dwarf planet was pushing material toward the surface. By the mission's end, in October 2018, Dawn had dipped to within 35 kilometers of the surface, close enough to confirm the deposits as sodium carbonate, salt left behind by evaporating briny water. A brine reservoir approximately 40 kilometers beneath the surface, hundreds of kilometers wide, was confirmed by gravity measurements. Some deposits were calculated to be less than 2 million years old, and because those salts still contain water molecules, the geological activity driving them may be ongoing today. The problem is that Ceres is too small and too far from the Sun to generate this heat by any mechanism scientists can fully account for. In a belt of cold rocks, drifting between two planets, something small and forgotten is keeping a liquid ocean and pushing it toward the surface. Whatever is keeping Ceres warm is doing so in silence, and we do not yet understand how. Number 7. The Flyby Anomaly. On December 8, 1990, NASA's Galileo spacecraft executed a textbook gravity assist maneuver, swinging around Earth to steal momentum from our planet's orbital motion and fling itself outward toward Jupiter. Engineers at NASA's Jet Propulsion Laboratory tracked it using the Deep Space Network, monitoring its velocity with extraordinary precision through Doppler measurements. When Galileo departed, it was traveling at the wrong speed, not by much, but by a very measurable, very real 3.9, 2 millimeters per second, more than every known force predicted. Gravity assists are one of the most reliable techniques in spaceflight. Engineers use planetary flybys to accelerate spacecraft without burning fuel, harnessing orbital mechanics with a precision that has guided probes to the edges of the solar system. The physics behind these maneuvers is not exotic. It is classical mechanics refined over centuries, tested thousands of times, and understood with extraordinary confidence. A small, unexplained velocity discrepancy emerging from a maneuver this well understood should not be possible. And yet it happened again. The Near spacecraft, during its Earth flyby in January 1998, emerged with an anomalous velocity gain of approximately 13.46 millimeters per second. The Cassini spacecraft, during its August 1999 flyby, showed a small anomalous change in the opposite direction. The European Space Agency's Rosetta probe, in March 2005, gained approximately 1.82 millimeters per second it had no right to have. Critically, the anomaly appears only during Earth flybys. Other planetary flybys do not produce it. Something about Earth's gravitational environment is interfering with these spacecraft in a way no accepted physics can explain. In 2008, JPL physicist John Anderson and colleagues published a formula that could predict the magnitude of the flyby anomaly based purely on the geometry of the approach angle and Earth's rotation. The formula works. It correctly predicts which flybys will show anomalies and roughly how large they will be. But the formula describes a pattern without explaining a mechanism, which in some ways makes the mystery worse, because a predictable anomaly suggests a real, systematic physical cause that our models are simply missing. The equations we use to navigate spacecraft are the same equations underpinning all of modern orbital mechanics. They have guided humans to the moon and probes to interstellar space. And at Earth, quietly, consistently, they are wrong. Number 6. Enceladus's impossible ocean. In the spring of 2005, instruments aboard NASA's Cassini spacecraft detected something extraordinary emanating from the south pole of Enceladus, a small moon of Saturn just 505 kilometers in diameter, small enough to fit comfortably inside the borders of the state of Texas. The moon was erupting. Jets of water vapor and ice particles were blasting hundreds of kilometers into space from a series of fractures near the pole, feeding material directly into Saturn's E-ring. A moon this size, this cold, this far from the sun, had no business being active at all. Enceladus orbits Saturn at a distance of approximately 238,000 kilometers, receiving sunlight roughly 100 times weaker than Earth does. There is no thick insulating atmosphere. The surface temperature hovers around minus 201 degrees Celsius. The moon is so small that radioactive decay in its interior, the slow heat of heavy elements breaking down over billions of years, should have been exhausted long ago. By every reasonable expectation, Enceladus should be as geologically dead as the cratered wastelands of our own moon. Nothing there should be liquid. Nothing there should be moving. Cassini flew directly through the plumes multiple times, and what it found reshaped the search for life in the solar system. Beneath the icy crust lies a global saltwater ocean, approximately 10 kilometers deep, with the ocean floor in contact with a rocky seabed. In October 2015, Cassini passed through the plumes and detected molecular hydrogen, a chemical signature of hydrothermal activity, the same process that powers the deep-sea hydrothermal vents on Earth, where life thrives in complete darkness. Complex organic compounds were identified in the plume material. Silica nanoparticles suggested water rock chemistry occurring at temperatures above 90 degrees Celsius. Scientists can account for some of the heat through tidal flexing, the gravitational kneading Enceladus experiences from Saturn and its neighboring moon Dione as it orbits. But detailed thermal modeling consistently finds that tidal heating alone cannot fully explain the quantity of energy being radiated, the intensity of the plumes, or the sustained activity over geological timescales. The heat budget simply does not balance. Cassini ended its mission in September 2017, plunging into Saturn's atmosphere. No dedicated follow-up mission has launched. A moon that should be frozen solid is venting a saltwater ocean into space, and it contains the chemistry of life as we know it. The source of the energy sustaining all of this remains, despite everything Cassini told us, incompletely explained. Number 5. The Pioneer Anomaly's Shadow. In March 1972, NASA launched Pioneer 10, the first spacecraft designed to cross the asteroid belt and study Jupiter up close. Pioneer 11 followed in April 1973. Both probes were masterpieces of precision engineering, and the Deep Space Network tracked their positions and velocities for decades using Doppler measurements accurate to fractions of a millimeter per second. By the early 1980s, engineers noticed something unsettling. The probes were not where they were supposed to be. Something was holding them back. JPL engineer John Anderson began a formal investigation in 1994. The anomaly was not random noise or measurement drift. Both Pioneer 10 and Pioneer 11 were experiencing an identical, steady, unexplained deceleration toward the sun, measured at approximately 8.74 times 10 to the negative 10 meters per second squared. The effect was tiny, but it was consistent across both spacecraft on completely different trajectories. By the late 1990s, when the probes had traveled more than 13 billion kilometers from the sun, they were roughly 400 kilometers closer to the solar system's center than all known physics predicted they should be, accumulating that error at a rate of 5,000 kilometers per year. The scientific community proposed explanations ranging from dark matter and modifications to general relativity to evidence for extraspatial dimensions. For nearly 20 years, the Pioneer anomaly was considered one of the strongest candidates for new physics in the solar system. Then, in July 2012, Slava Turishev and colleagues at JPL published a detailed thermal analysis in Physical Review Letters, concluding that heat radiating asymmetrically from the probe's nuclear power units was pushing back against their direction of travel, creating a tiny but measurable braking force. For Pioneer 10, the thermal explanation largely accounted for the anomaly. The case was considered largely closed. But the flyby anomaly, that separate, unexplained velocity discrepancy observed during Earth gravity, assists by Galileo, Near, Cassini, Rosetta, and others, follows a strikingly similar magnitude and pattern. It remains completely unresolved. The same instruments, the same measurement techniques, and the same level of precision that took 20 years to explain the Pioneer anomaly are the ones telling us something is still wrong. For 2 decades, the best-tracked objects in human history were quietly in the wrong place, and we attributed it to new physics. We were almost right about something being wrong. Just wrong about what? The question is whether we are making the same mistake again. Number 4. Jupiter's impossible auroras. On December 25th, 2023, NASA's James Webb Space Telescope pointed its instruments at Jupiter and captured something that its own science team is still struggling to explain. The auroras blazing at the planet's poles were magnificent, hundreds of times more energetic than Earth's northern lights, shimmering in the infrared with a brightness that should have had a clear and identifiable cause. Instead, they had no cause that physics currently allows for. Planetary auroras are well understood. Charged particles, accelerated by a planet's magnetic field, slam into the upper atmosphere, near the poles, and excite gas molecules into glowing. On Earth, the particles come from the Sun. On Jupiter, they come from multiple sources, including the volcanic moon Io, which constantly injects sulfur dioxide and other material into the Jovian magnetosphere. Scientists have been studying Jupiter's auroras since the Voyager missions in the late 1970s. And while they are more complex and energetic than Earth's, the basic physics was considered established. The Webb observations broke that assumption. The JWST team simultaneously captured ultraviolet imagery of the same auroras using NASA's Hubble Space Telescope, allowing a direct comparison across different wavelengths. The result was baffling. The brightest infrared features recorded by Webb had no counterpart whatsoever in Hubble's ultraviolet data. The two telescopes were looking at the same event at the same moment, and they were seeing fundamentally different things. Lead researcher Jonathan Nichols of the University of Leicester stated publicly that the observation has left us scratching our heads. To produce the specific combination of brightness detected simultaneously by both Webb and Hubble, the physics requires an extraordinarily large number of very low-energy charged particles striking Jupiter's atmosphere at the same time, a scenario that was previously considered essentially impossible given what we know about particle acceleration in planetary magnetospheres. No existing model of magnetospheric dynamics can generate the particle distribution this observation requires. The Webb data was published in May 2025, and no satisfactory explanation has emerged. We aimed the most powerful telescope in human history at the largest planet in the solar system, and the first thing it showed us was a light show that our current understanding of physics says cannot happen. Number 3. Planet 9. In January 2016, astronomers Konstantin Batygin and Mike Brown at the California Institute of Technology published a paper in the Astronomical Journal that proposed something extraordinary. A ninth planet, massive, distant, and completely unseen, was gravitationally sculpting the outer edges of our solar system. They had not photographed it, had not detected its light, had not observed it directly in any way. They had simply looked at the behavior of objects far beyond Neptune and concluded that something enormous had to be out there. The Kuiper Belt, the vast field of icy bodies extending beyond Neptune's orbit, contains thousands of objects on highly elongated elliptical paths, requiring hundreds to thousands of years to complete a single revolution around the Sun. A subset of these objects, the extreme trans-Neptunian objects, display a peculiar orbital clustering. Their paths are aligned in ways that Batygin and Brown calculated have approximately a 0.007% probability of occurring by chance. 6 hands on a clock, Brown described it, all moving at different rates, all pointing in the same direction when you look up. The odds against it being random are almost insurmountable. The proposed planet has a predicted mass of 5 to 10 times that of Earth, an orbital distance of roughly 400 to 700 astronomical units from the Sun, and an orbital period somewhere between 10,000 and 20,000 Earth years. Its gravitational influence, if real, would also explain several other puzzling features of the outer solar system. The detachment of Sedna-type objects from Neptune's gravitational influence, the existence of highly inclined retrograde trans-Neptunian objects, and possibly the slight 6-degree tilt of the Sun's equator relative to the planetary plane. One alternative hypothesis, proposed by Jakub Scholz and James Unwin in 2020, suggests the anomalous clustering could instead be explained by a primordial black hole, roughly the size of a grapefruit, captured long ago by our solar system's gravity. Extensive searches using the Subaru telescope, the Zwicky Transient Facility, the Dark Energy Survey, and Pan-STARRS have ruled out large portions of the sky where Planet 9 might hide, but have not found it. The Vera Rubin Observatory, now operational in Chile, may be the instrument capable of settling the question within the next decade. We have mapped every crater on the Moon, photographed galaxies billions of light years away, and sent probes beyond the edge of the solar system. And yet a world potentially more massive than Earth may be orbiting our own Sun, in our own solar system, and we have never once seen it. Number 2. The coronal heating problem. Imagine standing next to a campfire and feeling the heat. Now, imagine walking steadily away from it, moving farther and farther into the cold night, and instead of cooling down, finding yourself growing hotter with every step. That is precisely and bewilderingly what happens in the Sun's atmosphere, and it has been defying known physics since a Swedish physicist named Bengt Edlund first recognized it in 1939. The surface of the Sun, the photosphere, the visible layer that radiates light across the solar system, sits at approximately 5,500 degrees Celsius. Moving outward from that surface into the chromosphere, temperatures initially drop, as basic thermodynamics would predict. But then something changes. Rising further into the corona, the Sun's outermost atmospheric layer, temperatures climb with shocking violence to somewhere between 1 million and 2 million degrees Celsius, and sometimes far higher. In some active regions, coronal temperatures spike to 40 million degrees Celsius. The corona is not slightly warmer than the surface. It is between 200 and 400 times hotter, and it is moving farther from the energy source with every kilometer. There is no accepted physical mechanism that straightforwardly explains this. Basic thermodynamics, the same principles governing every engine, furnace, and star in the universe, says temperature decreases with distance from a heat source. The Sun appears to have never received that instruction. Two leading theories have been investigated for decades. The first proposes nanoflares, millions of tiny magnetic explosions occurring constantly at the solar surface, releasing energy that propagates upward into the corona. The second proposes alpha Venn waves, oscillations of plasma along magnetic field lines that carry energy from the photosphere into the corona and dissipate as heat. In November 2024, researchers at the Princeton Plasma Physics Laboratory published the first laboratory experimental confirmation that reflected alpha waves can heat coronal hole regions, a significant step. But the complete coronal heating mechanism remains unresolved. NASA launched the Parker Solar Probe in August 2018 specifically to investigate this problem. In December 2021, it became the first spacecraft to enter the solar corona, flying through the outer atmosphere of the Sun itself. It has now completed multiple coronal passes, measuring particle distributions, magnetic field structures, and plasma waves at resolutions never before achieved. Its data has ruled out several proposed mechanisms and provided strong support for others, but has not yet delivered a complete explanation. The problem has been under active investigation since 1939 and remains one of the most consequential unsolved questions in astrophysics. The star that warms our oceans, drives our weather, and makes all life on Earth possible is breaking one of the most fundamental rules of physics at its surface every second of every day. We orbit it constantly. We depend on it completely. And we cannot explain the most basic feature of how it works. Number 1. The solar system's missing fifth giant. There is a version of our solar system that does not look like this one. It contains 5 giant planets instead of 4. It is arranged differently, orbits differently, and feels, to a planetary scientist, like a more natural and stable configuration. That is the version every successful computer model of the solar system's formation tends to produce. Ours, the one we actually live in, is what gets left behind after something catastrophic was removed from the picture billions of years ago. The NICE model, a landmark framework for understanding how the solar system reached its current configuration, was developed in 2005 by planetary scientists Rodney Gomes, Hal Levison, Alessandro Morbidelli, and Cleomenes Tsiganis. It proposed that the giant planets formed in a more compact arrangement and then underwent a period of gravitational instability that scattered them outward to their present orbits. This instability explained the late heavy bombardment, the spike in cratering visible across the inner solar system around 3.9 billion years ago, the orbital positions of Uranus and Neptune, and the structure of the Kuiper Belt. The model worked. The problem was that it worked better with 5 giant planets than with 4. In 2011, David Nesvorny of the Southwest Research Institute ran thousands of simulations of the early solar system and published a striking result in the Astrophysical Journal Letters. Using only the 4 known giant planets, his simulations reproduced the current solar system architecture successfully in roughly 5% of cases. When he added a 5th ice giant, a world approximately 10 to 15 times the mass of Earth in a Neptune-like orbit, the success rate jumped to approximately 35%. The 5th planet was subsequently ejected from the solar system by a close gravitational encounter with Jupiter, flung out of the family it formed in, and sent drifting into interstellar space. A follow-up 2012 study by Nesvorny and Alessandro Morbidelli strengthened the case further, finding that a 5th giant also explained the orbital inclinations and eccentricities of the surviving planets more accurately than the 4-planet models. If the simulations are correct, this ejected world would be a rogue planet, drifting through interstellar space without a host star, cooling slowly toward absolute zero over the billions of years since its expulsion. Billions of such rogue planets are thought to exist in the Milky Way, remnants of violent orbital histories around other stars. This one would have formed from the same cloud of gas and dust as Earth, as Mars, as Jupiter. It would be, in the most literal astronomical sense, a sibling world, born alongside our planet, and then cast out into permanent darkness before life had the chance to begin on Earth. NASA's Nancy Grace Roman Space Telescope, expected to launch in 2027, may detect rogue planets by the thousands using gravitational microlensing. It cannot locate this specific one. We have no way to know where it went, how far it has traveled, or what it looks like now. The solar system's most important missing piece may be drifting somewhere between here and another star, carrying no light of its own, leaving no signal we know how to detect. We believe we live in a solar system of 8 planets. We have mapped it, named it, sent spacecraft to every major world within it. But if the models are right, we have been counting wrong since the beginning. And the true architecture of our solar system, the configuration it was born with, is not the one we inhabit. Something is missing. Something has always been missing. And it has been gone so long that the solar system rearranged itself around the absence, like a family that keeps the photographs but eventually stops setting the extra place at the table. If you want to see more videos like this, click the video on screen now and make sure to subscribe.